Hello maths fans! Dr. Tom Crawford here at the University of Oxford, and today we're looking at grad and div. The gradient vector and the divergence both require the calculation of partial derivatives, so if you need a refresher on this topic, then make sure you go back and watch the earlier video in the Oxford Calculus series where I explain what a partial derivative is and how to calculate one. We'll start with the gradient vector. Given a function f, we say the gradient or grad of f, which is written as del f, is equal to a vector. There's a big clue there in the name being gradient vector. And the first entry of our vector is partial df by dx. The second entry is going to be partial df by dy. And the third entry is partial df by dz. Now, if we think back to our definition of a partial derivative, it tells you how a function is changing in a certain direction. So the df by dx partial here is telling us how f changes in the x direction only, which means fixing y and z and moving in a direction where only x changes, so that has to mean moving parallel to the x-axis. This concept is perhaps most easily understood with a diagram. So suppose I have some general surface, and apologies in advance for the drawing here, 3D is hard. Something like this, so that would come down and then kind of go up and flatten off. Okay, so we've got some kind of surface, like so, and let's suppose that this is going to be my z axis for my height. I've got like a y-axis going into the board, and then we've got x going horizontal as usual. Now, if I'm calculating the x partial derivative, what I'm really saying is if I sort of draw in some more of these lines, then for the x partial derivative, I'm picking a point where I'm calculating the derivative. So let's take it to be here, for example. And of course, at this point on my curved surface, there are changes occurring in all kinds of different directions. So if this is in fact a dip, again, the diagram is not super clear, but imagine this is like a valley in my shape. Then if I move along the y-axis, so this is the y direction, across this valley, sort of through the valley, y doesn't change. Whereas if I'm moving in the x direction, which of course is horizontal, so this is kind of starting up on this downward slope through the valley and then coming up this way. So in the x direction, sort of following down and up that dip, we're clearly seeing a change in the gradient. It's going from negative through 0 and becoming positive. But in the y direction, going through or along the valley into the board, there isn't a change. If I were to walk along that line, there wouldn't be a change in that y direction. So by having partial derivatives, it allows us to represent what is happening on a surface rather than just a plot. So with the visual example here, I've just talked about the x and y derivatives at a point inside this valley. But of course, you could take a point anywhere on the surface, and you could even also look at how z was changing if you were to add an additional dimension. So again, these partial derivatives are just looking at how our function f changes when everything else is fixed, but we allow x to vary for the f partial, we allow only y to vary, just the y direction for the y partial, and we allow z to vary, we vary our height for df by dz, and everything else remains fixed. So really what this function, the gradient vector, is capturing is it's giving you the rate of change of f in your first coordinate as the first entry in your vector. You get the rate of change of f with respect to your second coordinate in the second position in your gradient vector, and the rate of change of your function with respect to your third coordinate in the third position of your vector. So putting this all together, we can see that the gradient function or the gradient vector tells us how our function f is changing in each of the coordinate directions, and therefore is a vector representation of the traditional derivative. Now, before we move on to the divergence, let's look at an example where we calculate the gradient vector explicitly for a given function. So suppose I have a function f, which is going to be a function of three variables, x, y, and z, and it's going to be equal to sine of x plus cos of y minus z. So as you can see, a function of x, y, and z. So our first step is going to be to calculate the individual partial derivatives. So when we do a partial derivative with respect to x, remember we treat the function as though everything else is constant except x. So we just simply ignore the cos of y. It's a constant, it differentiates to 0. Same for z. So we just have to differentiate sine of x, and the derivative of sine is cos. So the gradient, or the derivative in the x direction, is cos of x. Similarly, the y partial is going to be the derivative of cos of y only, so that's going to be minus sine of y, and then df by dz. That's the easiest of the lot. The derivative of minus z is equal to minus 1. So our gradient vector, grad of f in this example, would be equal to the first component in the x direction. How is our function changing in the x direction? It's exactly the x partial. So it's cos of x. How does our function change in the y direction? Well, that's just the y partial, minus sine of y. And then how does it change in the z direction? That's the z partial, which of course was minus 1. If we now set our function f to be equal to 0, then we can rearrange to get an expression for z as a function of x and y. So putting f equal to 0, we can then say that we have z is equal to, we're going to get sine of x plus cos of y. And now, having rewritten our function in this form, we can now actually do a surface plot. So if I open the Maple Calculator app on my phone, and then I click on the camera tool at the top, I can now actually take a photo of the surface that I would like to plot. Z is equal to sine x plus cos y. This will now appear in the app, and I can just click on 3D plot, and it will actually show me a three-dimensional surface plot of this function. So as we can see, this is a rather fun looking plot. I think it looks a little bit like an egg box almost. And importantly, we can actually see from the plot itself that we have this wave-like behavior. So if we were to imagine fixing the value of x on our diagram, so let's say x is equal to minus 100, and we were to draw a straight line and follow that path along our curved surface, then what we're actually doing is following a path that changes only in the y direction, because we fixed x to be constant. So along that path, we can see that we have this wave-like behavior as we dip into a valley and then come up over a hill and then through a valley again, and we continue with this pattern. And if we look at our gradient vector, it tells us that the change in the y direction is given by this negative sine function, and this is exactly wave-like behavior. The Maple Calculator app is an incredibly helpful tool when it comes to doing maths, as not only will it create amazing 3D plots like the one we've been looking at here, but it will also compute the various partial derivatives for you, which is a great way to check your answers. Download it now for free on Google Play or the App Store and see for yourself just how useful it can be. The divergence of a function is very similar to the gradient in that you calculate the same partial derivatives, but this time our input isn't a scalar function, lowercase f. Instead, for the divergence, we have a vector, which I'm going to call capital F. So we input a vector, let's say capital F is equal to F1, F2, and F3. So we have a three-dimensional vector that we input into the divergence or div, and the output is df1 by dx plus df2 by dy plus df3 by dz. So something that's really important to remember about grad and div is the gradient or grad, your input is a scalar and your output is a vector, but for the divergence, that's reversed. We input a vector capital F, which has three components, and our output is a sum of three individual partial derivatives. So this output here is going to be a scalar. It's a little harder to understand exactly what the divergence represents compared to the gradient vector. However, as a starting point, we can just look at what it is that we're calculating. So we take the x component of our vector field or vector function, we take the first component in the x direction and we compute how does it change in the x direction. Then we take the second component of our vector field and we compute how that changes in our second direction, which is y. And finally, we take the third component of our vector field and compute how that changes in our third coordinate direction. And then, of course, we add all of these things together. But to really understand what this means physically, we're going to need to draw another picture. So, suppose I have a two-dimensional, it's easier to draw, vector field. Let's say f as a vector field is given by x in my first component and y in my second component. Now if I draw a diagram of this vector field, now what this is telling me is that in the x direction we are changing according to the x value. So for example, if I go to this point here, which is a positive x and positive y coordinate, doesn't really matter exactly what, the sign is all that's important. So the first component here is x, which is clearly positive, so we're moving this way. And the y value is also positive, so we're moving this way. So overall, the direction of my vector is going to look something kind of like this. We sort of average out the vectors, supposing they're of the same size. We have some kind of diagonal or 45-degree angle. And again, if we were to take this one down here, following our vector field, then the x coordinate is positive, so I'm going to the right. The y coordinate, though, is now negative, so I'm going down. So overall, I am again moving diagonally away from the origin. And if we do this for the other two quadrants, you'll see over here, we end up moving in this direction, and down here, something like so. And what we've actually got here is some kind of, if I add in these ones as well, some kind of source. If you imagine this is a kind of fluid field or a source of magnetism, for example, there's something here, it would appear, that's sort of feeding everything else, and everything is moving away from this central point or this origin or source. So you could say that what we're seeing here is something which is diverging, hence the name divergence. And if we actually calculate the divergence, so according to our definition, the divergence, which can also be written as Grad Dot F, that's simply a notation, but it means divergence of f. Then we do the first component with respect to x, so dx by dx, well that's just 1, differentiate x, you get 1. So that's going to be 1, and then dy by dy, that's 1. So the answer here is 2. All we really care about is this is a positive number, because our fluid, if we interpret it as such, or our vector field, is diverging away. So it has a positive divergence. So the divergence is positive, so we would say that this is divergent. And again, you can think of this as some kind of, in brackets, some kind of source. Now if we change our vector field ever so slightly to the following, and let's say f hat, to emphasize it's different to our original f, let's suppose this one is now minus x and minus y. And again, let's draw a picture of that vector field. So this is telling us, let's do a positive x, positive y. So we're moving against that one, and we're moving down on y. So we're actually moving in like this, aren't we? So we're moving in like this. And now just to vary it, I'll do this one over here. So this is going to be negative x. So negative x minus of that means we're moving that way. And we're also on negative y. Minus that means we are moving positive. So overall, we're going that way again. And just as before, you can compute these for all of the quadrants. You'll see that this is coming in, this is coming in, this is coming in, this is coming in, this is coming in. So we have pretty much the exact opposite of our picture over here. Everything seems to be converging, moving towards a central point, much like some kind of sink or some kind of plug hole, if you think of it in terms of a fluid specifically. And if we compute the divergence, grad dot f in this situation, again, using our definition, we differentiate the first one with respect to x, gives us minus 1, plus the second one with respect to y, minus another 1, minus 2, and this time we just really care about the fact that it's negative, and this would be convergent, the opposite of divergent. And this you can think of as everything moving in towards a sink. So therefore, the divergence of a vector field is a way of measuring how divergent or convergent that vector field is. How much is everything moving away from the point where you've calculated the divergence? Or is everything moving towards that point, in which case you would have a negative divergence? I've actually included some further examples exploring the physical interpretation of the divergence function in the accompanying MapleLearn worksheet, which is freely available and can be accessed by simply clicking on the link in the video description. There are also some exercises on computing the gradient vector and the divergence for various functions, as well as an investigation of some of the further properties of grad and div and how they're related. If you'd like to explore MapleLearn beyond the free worksheets, then you can sign up for a premium account by using the discount code on screen, which will give you full access to everything the platform has to offer. Give it a go and let me know what you think in the comments. So now that we have a definition for the divergence and some understanding of what it represents physically, let's go through a couple of worked examples. So to begin with, suppose I have the following vector field. So let f be equal to 0, then I will have x, y, and then finally we will have y squared minus x, z. So we have a three-dimensional vector field, so we have all of the components we need to plug in and calculate our divergence. So we can say the divergence, or grad dot f, to use the shorthand notation, is equal to first component differentiated with respect to x. Well, the first component is 0, so we get 0 when we differentiate that with respect to any variable. The second component is xy, and we want to take the y derivative of our second component. So taking the y derivative, we treat x as a constant, because remember, we treat everything else as a constant apart from y. So x is just some constant. So clearly when we differentiate a constant times y with respect to y, we just get the constant. So that will be plus x. And then for our third term, we have the z partial derivative of y squared minus xz. So again, x and y are fixed, they are constants. So we ignore the y squared, that differentiates to 0, and then we've got minus constant z, which leaves us with minus constant. So that's not a plus, in fact, that's going to now be a minus, and the constant is x. So in fact, our divergence here is x minus x, so it's actually equal to 0. So for our vector field f, given by 0, xy, and y squared minus xz, we've calculated the divergence to be 0. And so what that means is the field, or the fluid, if you prefer to visualize things in that way, is neither spreading out nor being grouped together. There aren't really any sources or sinks. They could exist within the field, but overall they're kind of cancelling one another out. So overall the fluid is not spreading out nor shrinking and coming together. It's kind of all balancing out and leaving us with this situation where the general movement or spreading out of the fluid is actually 0. Now for our final example, we're actually going to look in a little more detail at where this notation, grad dot f, comes from in terms of the gradient function being represented by grad and grad dot f representing the divergence. So the first thing that we can look at is, what does it mean when you take a dot product between two vectors? So if I have A dotted with B, and let's suppose that A is A1, A2, A3, and B similarly is going to be B1, B2, B3. Then if I were to take the dot product between these two vectors, we multiply the first two and add them to the second two multiplied together, and then add on the third pair multiplied together. So A dot B would be A1, B1 plus A2, B2 plus A3, B3. So for a dot product between two very explicit vectors, we should hopefully be happy enough with how to compute this. But how does that translate to this operator, the divergence, when grad is an operator rather than a vector? So we kind of have to replace the operator, which is the gradient function. We need to replace it or represent it as a vector. So if we were to rewrite grad of f as follows, we might say that grad of f can be rewritten as a vector operator, which is going to be d by dx in the first component, comma, d by dy in the second one, comma, d by dz. And what we're going to do is apply all of that to f, where each one is going to hit our scalar f, and therefore give us the definition that we have at the top of the board. But by writing it like this, then what we're saying is that this is basically our vector operator, grad. And so if we use this as our definition for grad, again as a vector operator, then we can take the dot product between this and our vector f. So we can say, therefore, grad dotted with f is actually going to be d by dx, comma, d by dy, comma, d by dz. That's going to be our operator, the gradient, and then that's going to be dotted with our second vector, which is f1, f2, f3. And so if we now use the definition of the dot product that we have here, you take the first two things, multiply them together, add them to the second two, multiplied together, add them to the third pair, multiplied together. Then this, following that definition, is simply df1 by dx, where we have to use some kind of sensible way of defining the operator multiplying the function. So rather than multiplying, it's acting on the function. But you're taking the one in the first position and having it act on the first component. The one in the second position acts on the second component, and the third position operator acts on the third component. So we get df1 by dx plus df2 by dy plus df3 by dz. So this is where this sort of notation of grad dot f for your divergence comes from. Because what we're really doing is taking a dot product of this gradient operator along with our three-component vector, and when we expand out that dot product using the standard definition here, we get exactly how we've defined the divergence on the board. I've actually included an exercise in the accompanying Maple Learn worksheet which takes this kind of idea a step further. So what we're going to look at in the worksheet, or what you are all going to look at as the viewers when you go and have a go at the Maple Learn worksheet once you've watched this video, is the following. What happens if you do the divergence div of grad of f? We want to know what is that equal to. And I'll give you a little hint. Based on what we've just been discussing around this notation, we can interpret this as grad dot grad f, where the grad dot is going to be this operator acting on grad f. So grad f is this, and you just have to apply the gradient operator here to grad f written at the top of the board. So I really do recommend checking out the Maple Learn worksheet, having a go at this question in particular, as the answer that you get is something that I think you may recognize. Just click the link in the video description to head straight over to the worksheet, and don't forget, if you want access to the premium subscription service, then you can use the code on screen for a discount. Thank you everyone for watching. Please do remember to subscribe to the channel if you've enjoyed the video, and I'll see you all very soon. Take care.